One last example of being able to evaluate these trigonometric intervals involving sine and cosine is when we have these sorts of singular products, and we have these product to sum rules that we can use. And so these, again, are going to be some formulas that you probably want to have written on a note card, okay? So that way, when you go to do your problems, that you have all of these just right in front of you, and that way you're not flipping back and forth. And so we have that if we have sine A, cos B, where A and B are just some interior angles, then it's going to be equal to this sum and difference formula. But the one that we're looking for in the example below is going to be sine A sine B. It's going to be equal to 1/2 cos A minus B minus cos A plus B. Now, in this case, A is going to be 2x and B is going to be 3x. And so we could just immediately rewrite this as the integral of 1/2 cosine of 2x minus 3x minus cosine of 2x plus 3x. And we still have our dx on the outside. Now, what happens if we switch these around, right? And that would actually give us a completely different first term, right? That would become the cosine of 3x minus 2x, which would be cosine of x. But when we simplify this one, that's just going to be the cosine of negative x, okay, minus the cosine of 5x. All right, so the question is, and that's a negative right here, how come that's okay? Well, we have to remember that cosine is an even function, and that means that the cos of negative x is equal to cos of x. And so that's why we're allowed to just flip these around if we chose to. All right, so just kind of giving you, for those of you that might be using like a computer algebra system to check, or if you're thinking, well, what happens if I flip these around? Why do I get a negative instead of a positive? All right, so technically what we could do is we could rewrite this as 1/2 the integral of cos x minus cos 5x dx. Okay. And then finally, we can go ahead and evaluate these. Okay, so pretty easy to evaluate. Technically use substitution, but we just take the antiderivative of the 5x, which would be 1/5. So we end up with 1/2 the quantity of sine x minus 1/5 sine of 5x dx, distributing the 1/2 and plus c. Oh, there's no dx because we just evaluated the integral, excuse me, but there is a plus c at the end. And so we got to end up with 1/2 sine x minus 1/10 sine of 5x plus the constant of integration c. Okay, so be aware of these types of integrals where you have like a sine times a cosine, and they're not the same interior function, and so you can't necessarily reduce it a little bit. Right. So next thing we're going to do is we're going to take a look at integrals that involve secant and tangent. And similar to what we did before with the sines and cosines, if we have higher powers, we're going to start breaking off factors of tangent squared or secant squared or secant tangent. Okay, so this is a little bit of a new one. Okay, because before we might just break off a sine or a cosine, but it's good for us to break off pairs of secant tangent. And the reason we do that is because we remember that the derivative of secant is secant tangent. So if we can write the entire integral in terms of secant, save for one factor of secant tangent, then we can do a u sum. Similarly, if we can write the entire integrand in terms of tangent, save for one factor of secant square, then again, we could use a u sum. All right, so let's go ahead and take a look at a fairly elementary example of this. And then in subsequent videos, we'll take a look at more examples. So we have our secant x tangent, secant cube x tangent cube x dx, and we want to evaluate this. All right, so here's what we're going to do. No matter what, we can't even start to use any of these formulas, Pythagorean identities, unless we have a secant square or a tangent square. And so it might behoove us to break off a secant, and it also might behoove us to break off a tangent for this. Okay, so I'm going to rewrite this as sec square x tan square x, and then we're going to have a secant x, tangent x, dx. Now, if we can get the entire integral in terms of secant, remember the derivative of secant is secant tangent. All right, so if we use the u substitution right now, we could get rid of secant square, we could get rid of tangent x dx. We couldn't get rid of this tangent square. So here's what we're going to do. We are going to use a Pythagorean identity on tangent square and turn it into this sec square plus 1. So we have integral of sec square x times sec square x minus 1. And then we have secant x tangent x dx. Now, this is u substitution ready. We are going to let u be equal to just secant of x, because we know that the derivative of secant is secant tangent. So du is going to be sec x tan x dx, right? So this is our du, and each of these is going to become a u square. So now we have integral of u square minus 1, and then instead of secant tangent x dx, that's going to become our du, right? Before we integrate, we're going to distribute the u square. Not too bad on that one. So this is going to be integral of u to the 4th minus u square du. And now we can see this is elementary. Now we get u to the 5th over 5 minus u cubed over 3 plus a constant of integration c. Last thing we do, back substitute the secant. And so we end up with a secant to the 5th of x over 5 minus secant cube of x over 3 plus our constant of integration c. Right. So subsequent videos, we're going to do a few more of these, and then we'll be done with this section.